Hello, my name is Doris Baker, and I'm the PI on the MELVA S project. MELVA S stands for Measuring the English Learner Vocabulary Acquisition in Science. MELVA S has been designed for Latino English learners in 2nd and 3rd grade. All the items on the measure appear in English and in Spanish. Students can respond to the prompts in either language. The goal of the project is to develop a formative vocabulary assessment using automated transcriptions and automated scoring. Teachers will receive a report on student level of knowledge of words that are relevant to 2nd and 3rd grade science topics. With MELVA S, teachers can provide better vocabulary supports to English learners who are struggling in expressing their thoughts and ideas about a specific science phenomenon. Our theoretical framework is based on the acknowledgement that science is multifaceted and depends on 4 strands of scientific proficiency that include knowing, using, and interpreting scientific explanations, evaluating scientific evidence, understanding the development of scientific knowledge, participating productively in scientific practices and discourse. All these strands require the use of precise language. To achieve our purpose, we have worked on selecting the content of MELVA and developing the back end and the interface of the MELVA system. Nathan Gage, our tech expert graduate student, will talk more about the technology development. In terms of the content, words were selected based on the next generation science standards, the Texas Knowledge and Skills Standards, science programs, and teacher feedback. We have so far assessed approximately 900 students. Given the recent pandemic, we used for this assessment Zoom, through which a member of the research team coordinated the assessment with the support of a school facilitator. Students logged into the MELVA website, took a tutorial on how to listen to the prompts and respond to them. On this slide, you can see an example of a word and the choices students have to either listen to the responses, record, save, and go to the next word, or delete and re-record. To score the measure, we developed a rubric with examples for definitions and for sentences that also included a picture. Students could receive from 0 to 2 points for a definition of a word and 0 to 2 points for a sentence that matched the picture provided. This slide shows the dashboard that annotators use to record the progress in scoring student responses. We have achieved 0.8 inter-rater reliability, where 6 independent annotators scored the same student responses. Nathan is going to talk now about the creation of the back end of the MELVA S project and the interface. Before I pass the mic to him, I just want to acknowledge the PI team on the project, as well as key collaborators, students, and teachers. Thanks for helping us develop MELVA S.
Hi, I'm Nathan Gage, and I'm going to walk us through the infrastructure overview for MELVA. I handled the backend architecture. So this is the overall infrastructure. We're going to go section by section. The first section is what the students actually handle and the data that they see. The students have their pre-created forms that they are assigned, and the recordings get stored in Amazon Web Services on S3 and the metadata in a separate database called DynamoDB. We assign 24 pre-created forms to students, of which the students get 2 forms, which have 12 words each. So each student gets 24 words in total. We assign them by a particular algorithm where the first student gets forms 1 and 3, the next gets 2 and 4. And then once we loop around through all of our 24 forms, the next student gets 1 and 5, and so on and so forth, so that each word has a similar distribution of students responding to a particular prompt. Once the student gets their form, they see the 12 words from the first form on the top, and they can respond, record their answer, and submit their information to Amazon Web Services. Once they've completed all 12 words, they see this interface where if they've only finished their first form, they get a great job and have the opportunity to start another. Or once they've completed both of their forms, they say, great job, and you finished everything. And we found that this helps with student fatigue because they get excited once they're halfway through, and it doesn't feel daunting to do 24 responses as much as it does to do 12 responses. Next, once we've stored that information and collected it, we pass it on to our expert reviewers or our coders or our annotators in a interface so that they can nicely review all of the transcriptions and the responses and give them scoring. This is what the annotator interface looks like. You can see there's a transcription of the actual student response, which the coders can then listen to, correct, and also mark the language that the student responded in. This is really nice because then the annotators can go through and mark the particular aspects of the rubric that give the particular score for that student response, which allows us to train the annotated or the automated scoring model more accurately to give information about the contextual reasons as to why the particular score was given for that response. And finally, this annotator interface also allows them to mark particular issues with that response so that we can generate statistics about issues with that particular deployment, so that if we are having audio recording issues or students are responding more in Spanish and we have reviewers that only speak English or things of that nature, and that allows us to iteratively improve this interface for the students and the annotators alike. For our next steps, we want to continue developing the automated scoring model and compare it to the human raters to match the inter-rater reliability between the model and the human raters. And we also want to include that contextual information from the rubric to improve the automated scoring model overall. And to talk about that is Dr. Larson and Zhangdi.
So this next talk builds upon some of what was discussed in the previous talk. Well, here we focus on the automated scoring of the definition and sentence usage tasks, and this will jointly be presented by myself, Eric Larson, and Zhangdi Wu. So the motivation for why it's advantageous to use machine learning comes almost solely from the time that it takes for an instructor to review and score the student verbal responses. It can take hours to listen to these verbal responses and assign a score of that 0, 1, or 2. And that naturally kind of begs the question, with the advances in machine learning, especially for text processing, can machine learning models, reliably score students based upon transcriptions of their responses? So there's a number of challenges in using machine learning for this, as the kinds of free-form responses that students provide are both numerous and diverse. However, large language models have been quite effective at many language-based tasks, and so we want to investigate their effectiveness. So for the definition and sentence tasks, what we want to do is we want to take some forms of text input and assign them through an automated scoring model as either a score of 1 or a score of 2, say for the definition task or for the sentence tasks. But there's a lot of different parameters that can be set and need to be investigated for using large language models. For these language models, we need to provide text, but it's not clear what text from the student responses is going to be most effective for scoring. For example, in the definition task, we could provide the model with the student response, the word that they're being asked to define, and or the text of the actual word definition. And it's also similar for the sentence tasks. And then we want to score those responses using machine learning. So should we provide all of these inputs to the language model, or perhaps a subset of these would actually be sufficient for learning? So to investigate this, and which is efficient, we want to use an input factor analysis. Really, it's just clustering. The language model that we want to use is called BERT, and BERT is able to take input text and generate a vector of numbers from it, a 512-dimensional number. So it translates human language into a 512-dimensional score such that we can cluster the different outputs that exist. And what we would like to do is look at the different clusters that are found from the language model and how it corresponds to clusters of actual human scoring of 0, 1, and 2. And so we investigate different combinations of putting these inputs into BERT to see which is most reliable, and then cluster each of those combinations on the input texts and see if it corresponds in any way to the human scoring labels. So here is a two-dimensional clustering of each of the different combinations of student responses and the various words and definitions that we might input into the BERT model. In the top left, this is only using the student responses as input. The top right uses the response and true definition. The bottom left is the response and the word, and the bottom right is using all of the different texts as input into the BERT model. And these colors represent how a human scored the responses. So we can actually see that the best clustering visually is in the top right. The BERT clusters tend to separate the different scores. And what I mean by that is the different red scores that we see there are mostly in this cluster right here, we'd call it score 0. After that, a lot of the score 1s, the green responses, tend to be right outside the circle, and then right outside of those tend to be the ones that score as 2. And so based off of this analysis, we can choose to train our models based upon the student responses and the true definition, and this provides us the greatest clustering. or the best clustering so that we can have pretty good confidence that the model will be able to train based on this. Now, a similar conclusion can also come from the sentient tasks, where the best combination is the student response and giving the model an example sentence of the words being used appropriately, although the clusters are a little bit harder to see with the naked eye. So based off of this, we know what inputs to use. We want to use the student response and an example, the full definition, or an example sentence. But we still need a machine learning model to map from these clusters into a predicted score, where the next presenter will explain how that model does that.
Thanks, Dr. Larson, for the illustration of problem setup and selection of input factors. Now we have the two preserved input to the pre-trained model. We then construct a transfer learning that builds layers of neural network that leads to a dimension of 3 predictions. The reason for dimension of 3 is because the student can have a 0, 1, or 2, 3 possible different scores. The score is represented with a 1-hot encoding for training and prediction. The transfer learning architecture utilizes the design of residual connections as is shown in the left of the figure, the add branches. Residual connections shown by Amos et al. In 2017 makes the output of the network a convex function of the input. In this case, the vector representation provided by the pre-trained language model. This helps the convergence of the network. The output layer has a softmax function and is compared with a 1-hot encoded ground truth that is given by human readers. However, in previous studies, categorical cross-entropy was selected as loss function, which is also often a go-to option for classification tasks. In this problem, categorical cross-entropy fails to represent the quantitative relation between different scores. That is, distance between score of 0 and 2 is different from distance between score of 0 and 1. Thus, we adopted 2 more variations of objective values. One of them is to use a modified quadratic weighted cut-bias loss function shown by Jordi et al. In 2018. The other is to construct a multitask learning by adding another output layer. It has an output dimension of 1 and does not have an activation function. It calculates mean square error and have a weight as hyperparameter to upgrade the network simultaneously at the categorical cross-entropy branch. We also used weighted decay to help reduce overfitting, Adam as optimizer, RMS prop and stochastic gradient descent is also looked at, but Adam performs consistently better. The number of hidden nodes in each layer, the number of layers, the number of layers within the main flow of residual net are all hyperparameters, and the hyperparameter search was completed with Optuna. Overall, more than 5,000 networks were trained across different variations to find a good set of parameters and architecture. Here is a result of different models, including the previous pass and including the included elements on the left. We also did a 80%, 20% train validation split and a 10-fold cross validation. So this is a result for different models. There is not a clear overall winner. However, it is clear that the objective architectures that encode the quantitative relations between different scores have a superior performance with similar network architecture. Meanwhile, residual connections tend to improve performance further. We were also interested in finding how good the model performs on words it has never seen. We did that analysis by removing 2 of the words from the training and validation set, retrain the best model, and see how well they do compare with human readers. Here is the result. It is apparent that machine-human agreement is still lower than human-human agreement, which means further analysis is needed, but model does have a not bad performance on generalized to word it has not trained with. With sentence tag improve more when sum of words is introduced back to the training set. With the next round of data collection, there's a lot of methods and analysis we can look at. First is generalization analysis with more words. So if because of the previous data set, we only have 9 words, if we have more words, maybe the model can generalize better when they are performing on the words they have never seen. Second, additional analysis of pre-trained language model with more input components involved. Because next round of data collection, we actually ask students a question to request answers. So maybe machine will be able to figure out the relationship between that question and the answer. The third is latent space vector behavior and supervised contrastive learning, which refers to the figure that Dr. Larson showed. We want to constrain the space to make that different score cluster together more by the network computation. Last but not least is rubric-based classification. In the next round of data collection, we ask the raters to give a reason why answer is score of 0, 1, or 2, which I believe based on that classification, the model can separate different characteristics of answers better. Thank you.
Hi, my name is Joe Neese, and the title of my talk today is Prosody and Oral Reading Fluency Collection and Annotation. First, I'm going to talk about the foundation of our current project, and that foundation is CORE, Computerized Oral Reading Evaluation, which was funded by IES in 2014. CORE is a computerized oral reading fluency assessment framework that combines multiple shorter passages, automatic speech recognition, ASR for scoring, and the development of a latent variable psychometric model to produce model-based words correct per minute scores. Some of the results of this project include: 1, evidence to support the application of ASR scoring, as well as the use of shorter ORF passages read in their entirety. 2, the model-based words correct per minute scale scores had smaller measurement error than traditional ORF assessments. And 3, the model-based core scores had a stronger relation than traditional ORF assessments, with important reading outcomes like comprehension and state reading test scores, suggesting that our scores can potentially better help with identifying at-risk students and potentially help better monitor the ORF progress of those at-risk students, because the scores provide a better estimate of students' current and prospective reading proficiency. To take a quick step back, oral reading fluency, generally defined as reading quickly, accurately, and with prosody, is an essential part of reading proficiency. As perhaps the most prevalent reading assessment used in classrooms across the United States, measures of ORF are robust indicators of comprehension and overall reading achievement. However, these ORF assessments do not align with the theoretical definition of fluency, measuring only accuracy and rate, and neglecting prosody. Research has shown that measures of prosody explain variance in reading comprehension beyond measures of rate and accuracy, and that students with good prosody have better comprehension than might be expressed based on their ORF scores alone. The purpose of our current project is to develop and validate an automated scoring system to measure, unite, and scale the rate, accuracy, and prosody of oral reading fluency to be used as a screening and progress monitoring measure for students in grades 2 through 4. The first phase of our project was to develop a machine learning model to measure and score reading prosody. But in order to do that, we first had to collect human prosody scores to serve in the supervised machine learning model. Thus, the purpose of the task I will talk about today was to collect human ratings of prosody from a sample of existing ORF audio recordings from the previous CORE project. These human prosody scores would then serve as the basis of our subsequent effort to train an algorithm that could be used to automatically generate prosody scores from students' oral reading. We began with the prosody scoring rubric developed by NAEP in 2005, a 4-point scale that focuses on phrasing, adherence to the author's syntax, and expressiveness to assess prosody at grade 4. Although NAEP only applied the scoring rubric to grade 4, our research team made the decision to use the rubric across grades 2 through 4, independent of grade and based on the absolute prosody criteria specified for each of the 4 prosody levels. To help draw clear differences between the 4 prosody levels across grades, parts of the multidimensional fluency scoring guide, the MFSG by Rosinski et al., were incorporated into the original NAEP rubric. The MFSG focuses on assessing aspects of expression, phrasing, smoothness, pacing, and accuracy. We expanded and refined the NAEP prosody rubric with select parts of the MFSG to add more specific language and examples. A systematic process for adapting the NAEP rubric was conducted. First, 30 audio recordings were dispersed among the research team and scored individually by 4 faculty. These scores and commentary were documented, analyzed, and discussed. and a summary of the team's individual scores was presented, highlighting areas of agreement and disagreement. In our first go-around, 30% had the same score across all 4 raters. 43% had the same score across 3 raters, with the 4th rating different by 1 prosody level. 13% had 2 sets of identical scores that differed by 1 prosody level, and 13% received 3 different prosody scores. Based on the inconsistent variation within the team, it was decided that more in-depth explanation was needed for each of the prosody score levels. To do this, the team listened to recordings together during online meetings and iteratively specified deeper distinctions between adjacent scores using the MFSG factors of pace, phrasing, and expression and volume. The 30 audio recordings were again scored individually by the 4 faculty using a revised prosody rubric, not shown here, which improved inter-rater agreement. The team further refined the adapted rubric to clarify rating criteria and arrive at more unequivocal prosody scores. For example, the team added language about whether the overall storyline was represented by the reader. And after working through various examples, the research team added distinctions for each proficiency level from the MFSG, as well as distinctions based on the research team's professional judgment. So here's what that looked like. We took the NAEP rubric, shown here, and we removed parts that we thought were either confusing or could perhaps be improved upon. We then added parts of the MFSG that we thought added clarity and specificity, generally around pacing and expression, seen in purple text here. Finally, we added our own language, generally around coherence and expression, to help provide distinction between the 2 lowest prosody levels, seen in green text here. And this was the final prosody rubric shared with raters, including the bolded text shown here. A bit about our prosody raters. We recruited 56 raters across 27 states. 57% earned a master's in education. 70% were general or special educators or reading specialists. 88% worked at the elementary school level. And there's a link in the slide title with more information on the raters. 2-session training for prosody raters was developed for synchronous online delivery across 2 weeks. Each training session was offered twice and participants could attend either one. There was 1 week between the 2 training sessions. 3 members of the research team are present to deliver the content and answer questions using the slides and presented on the Zoom platform for web-based live interaction. All trainings were recorded for asynchronous training for participants who could not attend one or both of the live trainings. The 2 days of training included information about the project, a comprehensive review of prosody, the task of rating audio recordings for prosody for this project, an explanation of the rubric and how to rate recordings, how to earn certification as a prosody rater for the study, exemplar audios, and a practice exercise followed by a discussion of each reading and the qualities that made it a specific prosody level. We had 81 passages distributed across the 4 prosody levels that were identified and unanimously scored by the research team to serve as exemplars for training and demonstrations. The research team also created a website for participants to access training resources. The website included the 7-step process for scoring audio files, the prosody rubric as a resource to print or keep open when rating, training materials, including the presentation slides and a recording of each training session, 24 exemplar audio files from training session number 1, the link to the scoring site, and a page with information about a study. And there's a link in the slide title with more information on the training. The prosody certification assessments consisted of scoring 5 exemplar audio files, which had been previously scored by the research team. All 56 prosody raters met the prosody certification scoring by scoring at least 80% on 2 prosody certification assessments. So the 56 people who took certification number 1, 55% passed by scoring either 4 or 5 correctly. 80% of people passed certification number 2, 93% passed certification number 3, 67% passed certification number 4, and both people who took certification number 5 passed. And there's a link in the slide title with more information on the prosody certification process. For the prosody rating task, 6,096 audio recordings were rated by 2 different prosody raters for a total of 12,192 human prosody scores. The median number of audio files scored by prosody raters was 160, with a range of 38 to 747. And here we have a heat map to show how the two scores matched up. So along the diagonal, you have perfect agreement from scores of 1 at the lower left to 4 at the upper right. 61% of audio files were in perfect agreement across both raters. 37% differed by 1 prosody level, and 2% differed by more than 1 prosody level. Of the 2,250 audio files with scores that differed by 1 prosody level, nearly half were scores of 2 and 3. So prosody level 2 and prosody level 3. Thank you so much. If you have any questions, you can find me at jneese@uoregon.edu. And here you'll find links to both the project and the specific study I talked about today.
So this next talk will be jointly presented by myself and Yihao Wang. And here we're going to discuss the challenges in using machine learning based upon spoken passages from students. Whereas the previous talk discussed the prosody rating, there's also a measure of the words correct per minute that we want to be automatically assessed by a machine learning algorithm. So oral reading fluency is really the ability of a student to accurately and properly read aloud, typically measured through a human listening to the student read a specific passage out loud. The human listener is tasked with decoding the words spoken, and once that's completed, the words correct per minute has actually been shown to be a fairly good assessment measure that's suitable for guiding interventions. Now, because of this, a number of works that use speech recognizers try and automatically match the spoken text with a reference passage. But there are some challenges in trying to replace a human listener with a speech recognition system. Firstly, many existing approaches rely on training a model to recognize a specific passage of text. It can struggle with recognizing passages that it hasn't been trained with. Secondly, student reading aloud can have awkward phrasing and pronunciation that's pretty straightforward for a human listener to understand, but a speech recognizer really struggles with those types of errors. And finally, many speech recognizers autocorrect some phrasings that are spoken, and that makes it difficult to trust the output of the speech recognizer when you're trying to use it for counting words correct per minute. Now, all of these challenges can mean that a speech recognizer and a human listener are likely to give you slightly different words correct per minute, even from the same audio passage. In this work, we want to understand how big that difference is when using modern speech recognizers, such as the transcription services that underpin Apple's Siri and Amazon Alexa. Moreover, we want to create an automated algorithm that doesn't require training data from specific passages. So it could be used without needing to hear examples of students reading a given passage. It would simply use the noisy transcription from Apple or Amazon. And with this model, we also wanted to understand how we might be able to obtain characteristics of a student's voice, such as odd but acceptable pronunciations. And this last step is still a work in progress, but we will show some results today from modern speech recognizers. We used previously collected data that has had human transcriptions of about 13,000 recordings of students in 2nd, 3rd, and 4th. A human has already marked all of the words correct in each of these passages, and we can use that to evaluate our automated method. Now, we only report results on passages where students read at least 10 words aloud. Most passages are actually much longer than these 10 words, but we refer to those as reasonable responses. And for the methodology, I'll hand over to my colleague Yihao Wang.
Hi, everyone. My name is Yihao Wang. Thank Dr. Larson for introduction of the problem itself. I will introduce architecture and methodology to solve this problem we proposed. First, we using something called the LCSS algorithm, which is longest common subsequence. First, we put the transcription to put the audio to the Apple transcription to get the transcribe of that passage, and we'll retrieve the time information and what word is spoken. And now we have a ground truth text, and we compare the output from transcript server and the output from the ground truth and to using the longest common subsequence to match in the maximum word is possible. So it's a very well-known algorithm in computer science, which can get the maximum output from the given two taxes. Then we calculate the starting point of the first word and the ending point of the last word to calculate the time when time difference of the word being spoken. Then we calculate the word correct per minute. So we use that as a raw input, and we will improve that method later. To improve that method, first we also need to know what audio should sound like. So when given the reference text, what the reference text should listen, and what is the frame look like. So we put that ground truth test to a text-to-speech server and to make it as the audio. Then we send through the same transcribe server to get the tagging of the time and what word is spoken. Then we run the LCS algorithm to match the pair. So we can know what the test should should look like and what the student actually spoken. Then we also calculate the MEL spectrum to represent this word and the frame of the whole passage. So the first part, and we send these two part of message to the network simultaneously. So it will be the same architecture, but sent into a different input. But the input actually is the same sentence. So then we can compare the difference of them. The first part of network is actually frame-based feature extraction. So we use something called the UNet. It's called the UNet because it's very look like a U. So it's going from the larger representation to the smaller representation, then go back to larger again. And to do that, we can achieve multi-resolution feature of the frame is spoken. So it's called multi-resolution because sometimes the word is short, sometimes the word is long. So we want to process them at the same time. So we use this method. And the UNet is also a well-known method in computer vision. So we just using that idea and repurpose it into the audio field. And after we obtain the feature, so we can using the tagging information to get statistic within that period. And then we send into the second network, which is attention-based to prediction the relationship between each word. So once each word is clasped into one feature, so we can compare the difference of them. And after that, we should conclude that in the deep space or after several network for several layer of network, they should have an identical representation, which represent the same word. So to do that, we need the same representation to be as close as possible. But if they are different, we want to they are far away as possible. We achieve this by introducing something called a contractive loss, which enable us to do this job. And for the final part, once we have the deep feature, which is related to the word, it's a natural thinking that we need to decode this word to recover the text. That will introduce reliability of the whole network, and also predict what word is exactly spoken. Here's some result of our first output of the longest sequence LCSS algorithm, the longest subcommon sequence. So from the result, we can see if we using the reasonable response, which is longer than 10 words, the average difference is 15, which marks MAE. So average speaking, there are 15 words different from human transcription and the machine transcription. But if we consider the middle 60, which is we kick out the worst 20% and the best 20%, so difference is about 10 word difference. So that means there are a lot of outliers need to be figured out in this algorithm. And we want to improve that using the method we proposed earlier. And this is also a part from the output. So if the human output is identical as the machine output, the scatter dot should be in the straight line. But it's not because it have arrow. And we can see the arrow is separate on the top and the bottom of the line, and it's have very consistent performance from the low to high. So that and in the later, we want to make it as narrow as possible. So we want the difference of from the true word as small as possible. That is a future work we can do. First is implement the algorithm to see what the result it should be. And also we want to investigate the feature map. So which first is, can we get another feature from the word-based feature or the frame-based feature to understand the student speech? Not just how many words they speak is correct, but also another prosody features. Thanks.
So, welcome everyone. I know there's a few people. I'm going to give just a couple of minutes here, or maybe 1 minute for people to jump in from the end of this session, and we'll get started. And do feel free if you want to show your video, so it's more of a discussion that we can go back and forth for this. I know it's been a little bit different in some of the panel sessions, so if you do want to show your video, and I think it'll facilitate a more interactive session rather than us just talking at you.
Yeah, and if you want to start putting questions in the quick Q&A or the chat, please do that.
I think to start things off, what we can do is, potentially start with questions that were centered around the automated scoring for vocabulary acquisition and for sentence usage of STEM-based words. And we can start with those, and once we get through a few of those, maybe when we get here about 40 minutes past the hour, we can, I'll turn it over to Joe to do a bit of an overview of the prosody and oral reading fluency data collection that was done. And that maybe will provide also a little bit more context to the final talk, which actually talked about methodologies and results that were related to that data collection effort. So if anyone does have questions, please feel free to put them into the chat box. Try not to use the Q&A feature. If you can remember to throw them into the chat, and we're happy to answer any questions that might be there. And while we are getting started, I might put one of the first questions that's, I might go ahead and start us off on a discussion here. I know that one of the questions that we've been asked in the past are what aspects of the annotation and rating were really most helpful for obtaining reliable scores among annotators. So this would be related to the vocabulary acquisition, where we have multiple raters that are listening to student responses and giving them a score from 1 to 4 on how they've actually used that word in a definition or used that word in a sentence usage. And I might ask Dr. Baker, Doris, do you want to handle a little bit of that discussion, and I can add to it as well?
Sure. Yes. Yeah. So one of the first things we looked at was at developing a rubric that would be as easy as and comprehensible for all the scorers, independently who they were, to score the annotators, like Eric was saying, to score student utterances. And so we went through several iterations of the rubric to kind of really find out specific examples that would be illustrating what for example, a 0 points meant, or a 1 or a 2. And then we practiced it with a group of our team to see if it worked, if it made sense. And then based on that, we just kept kind of doing several iterations. But I think that the rubric is really what, for us, when we are scoring this type of assessment, is very helpful. But I think also for the technology team, it really helped us connect the content with the technology by focusing on the rubric and really thinking through all the potential responses and what the responses meant for each of the points that students were receiving.
And one interesting thing that we might point out with that too is that in our rating software that was created, one of the things we started with was simply having annotators come in and rate some of the responses on that 1 to 4 scale, but they didn't necessarily provide us with a strict reason for why they rated it a 1 or why they rated it a 2. since that time, we've actually added that ability, and you saw a little bit of it in the panel discussion, where when they select a 1, they also have to select what's the overall reason that they think, or what's the most proximate reason why they rated it a 1 or rated it a 4. And since we've done that, we've actually noticed that our inter-rater reliability has jumped quite a bit from providing that. So before we had that integrated, we were getting, it's a smaller sample size, so it's not an apples to apples comparison, but we were getting inter-rater reliabilities around 0.7 or a little higher. Once we added the reasoning into that, we're actually now getting, inter-rater reliabilities that are, well above 0.8, many of them 0.85 or so, which in our community, we would consider excellent agreement.
Yeah, and just to expand that a little bit, we really had them go back like to the rubric to explain their answers, and so therefore, if they didn't find in the rubric an explanation that made sense with what the score they gave them, we kind of changed it. No, we made transformations to the rubric to make sure that they would match. And of course, we have like 16,000 or 20,000 utterances from students. So, we can't capture everything in one rubric, but we did try to capture the main ideas of what each score meant.
And I'll give a quick opportunity if anybody wants to put a question in the chat. If not, I can provide one as well. Okay, well, I'll throw another question in the chat here. And actually, Dr. Baker, I'm going to relate this one to you as well. I know one of the things that used for these automated assessments, how receptive are teachers to having, a machine learning come into, even though it might be a bit more scalable, they can look at, problem cases a bit more often. How receptive do we know that teachers are to having some of these automated assessments be used in the classroom?
Yeah. Well, from recruiting and our experience, teachers really are looking forward to that. They think it's a really great help for them to reduce the time that they would take scoring this type of assessments, but also how to guide and prepare then and teach. How can this type of curriculum-based assessments basically really reduce teachers' time in terms of thinking about what to focus on. No? So our idea with the Melva S is that if the teachers should spend as much time as possible teaching science, doing hands-on activities and model demonstrations with the students. But then, what we found is that the language is always missing, and so can we provide students, or at least teachers, with an idea about how well students know words, and based on that, they can also introduce that in their during instruction. So they wouldn't need to focus everything on words and how to define words and how to use them, but they can practice science, but at the same time be aware of how much students really know the words. And one of the interesting things that we found is that because we are working with Latino students, is that a lot of the students really take or define the word and use sentences that are based on the background knowledge. So we have found some interesting things about, for example, students watching a show after they come back from home, and that one of the words that we had there was impact. And that show, it just so happened that it's called Impacto in Spanish. And the students watched them. So all their examples, when we asked them, well, can you define a word? Can you give me a sentence with a word, were connected to that show. And I think that is, it shows that the students know something about the word. It's not like they don't know anything, but they are missing it maybe in the context of science. And that's what teachers can do. They can see where students are in terms of their understanding of words, and then bring them to the level of more scientific definition and use of the word, so that they can really benefit from that learning in the past, but also improving their own science outcomes.
Great. And we do have a question in the chat here. So the question is, how well does the system handle varieties of dialects in each of the 3 types of tasks? Does it report back anything about the dialect of the speaker? And so I can start a little bit with that. One of the things that we have done with both of the projects is, there are a considerable diversity of dialects that students will answer. There's also all sorts of problems with things like background noise. Like a lot of these recordings happen in a classroom setting, and there's lots of things going on at the same time. And so one of the things that we have done is used a technique that's called augmentation. For the training of the data that we have. So essentially, when we use some of these commercial speech recognizers, they will come back with what it thinks the verbal response was. However, it's many times not very good in that. And so because we are training with some of that noisy data of the transcription, we use that transcription and then actually provide the transcribed words to another model. So that other model can actually handle a bit of noise and errors that will happen in either the phrasing or some of the common dialects that may cause problems for automatic speech recognizers within that. And so by training with that noise, we can mitigate it. And it also it's a nice mirroring of the way something like this would actually be deployed, because the speech recognizers that we're using for this, they're the state-of-the-art speech recognizers. They're the ones that would underpin things like Siri and Amazon's transcriptions. And so those are unique challenges, and we haven't quite noticed specific dialects that don't work well, but we do need to dive maybe a bit further into that data before I concretely say that it's not influential right now. And on the other side of that, I would also say that one of the things on the oral reading fluency, I know we haven't talked too much about what that is, but on the oral reading fluency side, we actually we provide inputs into the system that are based off of different ways that you can use text-to-speech synthesis. So if you've ever used your, Siri, and you've asked Siri to be on an Apple recording, if you've ever asked that to be a different dialect or a different accent, we've done a lot of the same types of things to provide a lot of different ground truth sounds to the model itself, so that when it's trying to do word matching between what the students say, the ground truth that it's trying to match again is not just one dialect. It's actually many dialects that we have some control over from the speech synthesis. But we do have a few questions that are in the chat. And so one of the questions that we had is, have we thought about how students use knowledge of genre and domain related words, and how that could be related to the quality of their oral discourse? And I think that's a great question, actually. Doris, I know we've talked a little bit about this in the past. Do you want to take a quick stab at that one?
Sure. Yes. Yeah. Exactly. I mean, this is definitely the reason actually we're doing this project, because what we found is that, in the previous work that we have done, is that students would get a lot of ones, right? So one, and the scale was 0, 1, 2, and the reason I think is because they know a little bit about the word, they have heard it before, but they can't kind of express it in the science kind of genre within the domain. So that's where we want to capture. We want to see how that is connected to actually their writing and their expressive and their oral expression. So we can then guide it and again provide additional supports if needed for them to have a clear vision or understanding of the words in science. So yeah, that's what we are exactly studying right now. And in terms of the technology, I think, Eric, we have talked about that, about how the system captures those syntheses that sometimes, the sentences that sometimes are not maybe syntactically correct or are lacking more explanation.
Yeah, no, exactly. And what's nice about this, because we, in analyzing those vocabularies, it is interesting because we used a large language model, similar to like a chat GPT, but more on the side of analyzing and taking in some of the words to generate how, if they've used a word in context or if they're using it properly in the sentence. And there is a lot of variability on that, and it comes with a lot of context that might be different among the students. And so it's one of those kind of daunting problems that might be there. But with the advent of large language models, one thing they do well at is processing a diversity of words similarly, so that context is actually provides a pretty good baseline for us to use for that. And then let me get to the next question. Oh, how well? Okay, so this one is related to more on the oral reading fluency. How well could the system handle parts of speech that aren't grounded in whole word recognition? For instance, wanting to implement a tool like this for scoring accuracy of students, for blending and segmenting letter sounds. That's a great question. I know that there's been some work in the past that use phonemic level matching. I think that's one solution to this. And it's actually a pretty good solution. One thing that we have noticed in our work is it's not just the phonemic level matching. There are sometimes, words that the student did read, they got pretty close to, but the phonemic pronunciation was a little bit off. It comes back as the wrong phoneme a lot of the time. And so that's why, one of the things on the machine learning side that Yihao has been working on is really how do we embed the word sounds into a kind of consistent level. And so our approach has actually been trying to merge together and do some of the word matching based off of the way that students have said it, and also text-to-speech synthesis to try to do some of that matching along the way and give the model a lot of examples of, okay, these are pronounced differently, but they should be marked correct as the same type of word. And then also push words that are further apart, the ones that are actually merged as incorrect. So I think in our experience, that helps really well with word matching, but it doesn't necessarily help with detecting that segmentation or blending has happened on that side, which requires a bit more. I don't know, Joe, did you want to say anything more on that side, or?
No, I think that's a great answer. I think I saw the comment. Yeah, there are some commercially available software. I think Deborah Reed said, yeah, they provide phoneme whether at the phoneme level, so you can score it at that level. I don't know how accurate those are, how those do, but I know, for example, Soapbox does that.
Let me see here. Another question. So have we considered some matching of prosody to skilled expert reader patterns rather than human raters who don't seem to totally agree with one another? It's like a distance metric or such. Joe, do you want to take a stab at that one?
Yeah. John, I really like that question. Can you say more about like what you mean by like a skilled expert reading pattern, how like that's determined?
Well, I mean, even Siri, when it reads my text out loud from MS Word or whoever, I don't know who's reading it, it sounds pretty fluent. And there's basically a set of patterns, acoustic patterns that in fact, we've done studies where we look at kids reading in comparison just to look at the pattern of flow. And it's as if the better reader they get, the more the pattern's a little stretched because they're slower, but the same sort of frequencies of movement are available. So I'm not an acoustic engineer, but I thought that might be a way of thinking about prosody. The trick is, of course, different readers might have different patterns, so you'd have to get some sort of mean. Yeah,
I think you can totally, you don't need human raters to score prosody. You can extract so many features from those audio files to estimate prosody. But I'd still say, I'd still in terms of like, how do you know it's good prosody? You still need a model, right, to say like this is good prosody. Like, but there's basic features, even like the silence between words, that that's a pretty good measure of readers' ability. So I think, like I said, there's many features I think you could use. But still, when you say like you listen to Siri, like that's good prosody, you're still saying, hey, that's good prosody, right? At some level.
So yeah, you're going to have to still get agreement that the skilled model. So it's similar to the idea that you put in the sentence that made sense, that you thought was an exemplar. It's you have to get several exemplars of quality reads, and then but use those as your base rather than agreement on how bad it is from humans.
Totally, yeah. I still think it's a supervised model in this case, right? You still need some sort of judgment at the end, but yeah, totally. You don't need a human to say this is good, or a rubric developed by, the reading experts. You can figure that out entirely from the features. And I think, Eric and his crew can talk about the I don't know, thousands of features that you can extract from the audio data.
Yeah, and to be clear, we so you're right. So the features that we pull out, they are there. There's hundreds of features that are pulled out that are typically used for prosody rating. Those have to do with pitch, intonation rises over the sequence, with a little bit of things like shimmer in the words, the pausing, and those that are used. So we have that's there. And I think to your point, it's can you use that and come up with a deterministic model of this is what good prosody looks like, and then kind of measure, does it deviate from that, where we've used machine learning as that label to say, okay, where it may not be clear exactly what that mapping is. So it's more black box approach.
Thank you.
Great. Yeah, they're great questions. Appreciate them. Okay. So I wonder if we might talk a little bit about, so I know that we had done a little bit. I wonder if we might talk about how students perform that are where English is not the primary language that they have. So I know that we've gotten questions in the past too about how students that may not have English as their primary language, if this is amenable to be able to use when students may answer, let's say for instance, we're in Texas, so we would typically see Spanish that comes across as another type of response. And that's actually, so that's something that we're currently working on. I don't have a definitive answer for how well you can do automated scoring for this, but we do have a hypothesis that a lot of the automated scoring methods that we've developed for English learners can actually be adapted as well for students that maybe primarily speak Spanish in the home by using bilingual embeddings of the words themselves. And so essentially how we translate the word into the numeric structure and then learn from the numeric structure. There are some embeddings that similarly will take words in English and words in Spanish and put them to similar contexts and vectors. And so that's one of the things that we do want to look at in the future, is because we have a large range of students that have responded completely in Spanish. And so we have the English equivalent and the Spanish equivalent. So we think we have a unique opportunity to see how well some of those multilingual embedding structures might work for some of those students. And I know, Doris, did you want to add anything to that? Because I know it's a pretty common thing that we see in the school districts.
Yeah, and I think that it's really exciting too, because not only can we see have students responded in Spanish only or in English, but then some of them also combine both, right? And so it will be interesting to see how those students that are using really both their assets, their English and their Spanish assets, they respond and understand science concepts, and I think this opportunity of being able to, clearly leverage the technology to understand that is really going to enrich, I think, our support for English learners and what they really need, and how they understand the world, with those two bilingual kind of experiences together. Yeah. Yeah, and the assessment, in fact, we use the Melva. We gave the students could choose the translation, and every word that they saw was done in Spanish and in English. We knew that there would be differences in the meanings, right, of some of the words. For example, the word inventor means something very different in Spanish than it means in English. In Spanish, it means telling lies. And so we could see also how they used inventor, not just for somebody that creates something new, has never been done before, but also in the context of, my brother invented that I went to the store, something like that. No, and they were not. It wasn't true. So it's kind of like that unique opportunity we have now also to see that and explore that part more.
And I know that we have seen when we ask students to essentially use a word in a sentence, the diversity of responses for using a word in a sentence is really quite broad. So much so that sometimes, you know, our human raters would have a little bit of difficulty even agreeing with one another and did they use it in a sentence correctly. And so, you know, since that time, one of the things that we've done is built into the interface and that you saw was to provide a picture for the students to be able to say, okay, use the word in the context of this picture. And by narrowing that scope a little bit, but still allowing the students to have free form, you know, sentence usage responses, I think we've been able to increase that reliability among, oh, did they use it properly or not? It's a bit easier both on, you know, for us to rate it, and because that consistency, I think we're also seeing the machine learning is also having a bit easier time in judging that context because of the kind of narrowed diversity of some of those responses, which has been, at least on the assessment side, a good thing because it's easier to assess.
Yeah, the challenge is always finding those pictures, no, that really represent what we want to, in abstract word like analyze or observe, but and at the same time, you know, have students produce sentences that make sense, and yeah, so. But I think we have refined it, and again, we have gone through several iterations and changed some of the pictures that we did not think. I mean, that we did not get a response or so to improve it. Yeah.
Well, I think we might be coming up to time on the session, but if there are any last minute questions that the others wanted to ask, we're happy to answer them. Or if people do have questions where they they didn't get a chance to in the session, to please feel free to email any of us, any of the panelists. We're happy to respond and talk to those. Oh, I'm seeing that we actually have 15 more minutes. Okay, great, good.
Oh.
I think we moved from an hour session to an hour and 15 session, and I flubbed that a little bit. So we do have a bit more time for questions if anyone does have something they'd like to place into the chat. Well, I'll take this downtime to just make sure that we've thanked the institution IES for all of the support that we've had. I think this has been really a wonderful collaboration on this side, and I'd just like to acknowledge that collaboration wouldn't have been possible without the support there.
Yes, I agree. This is a great opportunity, and it's kind of, and these are projects that were completely independent at some point, and now, you know, we can see these connections and ways of really collaborating that will probably increase, you know, the knowledge and understanding that we have about this fluency assessments, right, or CBM assessments that I think goes a little bit beyond what we have done before. So it's exciting to work with everybody here, with the teams.
I have a thought I could just, since we seem to be in a lull.
Yep.
So words correct per minute is a perhaps peculiar and error-related estimate of how long it takes to actually read a text. So it's not a one-to-one correspondence between, say, the length of the words or the frequency of the words and the time it takes for a speaker to actually read it out loud. And I know there's one paper I can cite that looked at that. Is there anything in your work that allows us to maybe, you know, move towards a more accurate way of thinking about the metric versus words correct per minute? Do you understand what I'm getting at?
Right. So because it can be inconsistent depending on the length of words that are in a passage that may be there.
Not just length, but also co-articulation. So
Yes.
given two passages that are 100 words long, average speakers will actually spend different amounts of times reading them aloud. Skilled readers.
Right. And I think that, and Joe, you can correct me if I'm wrong on this one too. Some of this was related to kind of the logistics of the data collection as well. When this was done for a lot of the human raters, they were sitting down with the student, and they would have form sheets that they would be able to do kind of words correct. So I think that's where the words correct per minute comes from. And we kind of adopted a lot of that, but it's more of a logistical constraint, I think, with the data collection than it is with, oh, do we trust that measure more than another? Because I think you're right on point with this comment, is that there may be other measures, and there probably are other measures that we could be looking at here, such as just words correct per passage, the students, and giving them a bit of time, and that may also reach a broader level of fluency for us, and give students an ability to show some of that fluency on longer passages. But Joe, did you want to add to that as well?
Sure. Yeah, I have a few thoughts. I think one thing we are doing, or maybe this kind of approximately talking about, is by adding prosody. We have a good measure of prosody. It will no longer, I don't think it can stay on the words correct per minute scale, right? We're gonna have an arbitrary scale. So hopefully, we can say, reduce that measurement error in estimating reading ability, something like that. So that's kind of a different scale, and could help. Another thing we try to do to address that is like equating passages. So if you have 200 word passages, they're different in, say, difficulty, right? If we can kind of equate these scores, it's going to reduce some of that measurement error and kind of estimating student ability. I do think words correct per minute is a useful scale, right? It's not perfect, but there's certainly like our first project, let's kind of reduce some of that measurement error around it, get a little more precise score. And I think we've tried one way to do that, and it seems to be all right. Work pretty well. But a couple of reasons it's useful is, like, teachers understand it kind of implicitly, that scale, that words correct per minute. So if you give them a number, they kind of understand where that student's at really quick. It's also like, for a minute measure, it's got some pretty good technical adequacy, right? Again, like, there's huge deficiencies, but we try to address those, but ultimately, like, not bad for a really quick measure. But yeah, tell more, like, what are you thinking about? Because I think it's interesting. I think there's a lot to critique about it, but what do you think about, like, other possibilities or different, like, options, or yeah.
I think I agree with almost everything you've said about the practicality, and it's nice to give a metric that's real as opposed to an arbitrary scale. But I think that the pressing of this notion of equating as if it solves the problem by thinking of a word as a standardized vocal unit, even when you take into account difficulty and length and other things, because speech just doesn't perform that way. I mean, on a written page, the graphemes define the length, but when it turns into speech, there's a transform there that isn't always one-to-one. And I'm thinking, because you have all these wonderful technologies now that we're learning to understand the acoustic form, we can start to think about how to take advantage of that and not make it seem, give this false illusion that you can equate passages. I think that's my issue. I don't think they're equatable in the way that we've constructed or led people to believe. At least not when they are transformed into oral speech, and probably not when they're transformed into comprehension either. So.
Yeah, I see what you're saying. Yeah, certainly.
So maybe down the road, you'll find things in in the way you're doing it that allow us to still call it, this is how long it took them to read, but not give the illusion that that perfectly equates to each episode or each text, as if those are, you know, equated in the traditional assessment sense.
Yeah. That's true. I mean, yeah. I don't know how to get around measurement error in most cases. Eventually, right? You're gonna let some. But yeah, and I also think it's important to think about like how they're used, and what interventions. Well, what do you do with the data? So we get real precise. Well, still, the question always remains: well, what are you going to do? How do you teach fluency directly, or these other skills that kind of build up to a fluent reader? Things like that. Yeah.
Thank you. It's really been a fascinating session. Thank you.
Thank you. I really appreciate your questions. Like a few times a day. Yeah. Thank you for asking, talking.
Well, I can maybe one of the other things that we could answer here. We're coming on to just a few minutes left. But I wonder, are there other speakers that wanted to comment on, you know, potentially some of the maybe limitations or some of the challenges for the machine learning aspects?
Well, I think that maybe one of the things that we have talked about is a report for teachers. No, like we want to give teachers something, information about the scoring of the MELVA assessment, so that they can guide their instruction. And that is something that, you know, we're still working on, right, on different ways of providing teachers the information. But I think a challenge will be to make sure that they really use it. No, traditionally, what has happened with many of the CBM measures is that teachers are trained to do it, they use it, but then they put it in the cupboard and are not actually using it for instruction, but it gets lost. And so I think that our challenge is to really make sure that they find this assessments useful and they're effective in terms of guiding their instruction, so they can actually use them. And we think that a report that is automatically generated, so teachers don't have to turn to enter the data, or they don't have to summarize it or examine it, but it comes in a format that helps them use it, then I think it would be a great opportunity for us all to learn, for them to also guide their instruction. But it's not. I recognize it's challenging. So.
And to build on that, one of the things that we've also discussed is that, you know, on top of that, there can be automated measurement errors that also are things that need to be conveyed back to teachers and instructors when it's likely that, or we don't trust the model output. That needs to be conveyed in a way to make sure that, you know, how often that occurs, and to be able to let them know that, you know, there may be some false positives that are happening in part of the system, because I think it would be naive of us to think we're going to get a perfect automation of some of these things. There will be a few errors, even if they're not common.
You foresee something like error bands or risk around particular responses to say, well, we're less confident about this, or flags that, you know, that the machine scoring didn't perform the way you're, you know, a confidence interval.
I do. I certainly do. I think a self-competency on that. The problem right now is a lot of machine learning models are overconfident. And so, you know, using their confidence to judge what it looks like is not a perfect, but there are some methods that could be done. And I do think it's a really interesting research topic, because if this is something that teachers are going to use, we have to build trust for that. And the best way to do that is to really be transparent about the model and its abilities.
And is it being used, like, how is it administered, in the sense that a couple of students at a time go off to you know, tablets or whatever and read into it, or or use this whole group, or, I mean,
yeah.
What's your
Doris, do you want to take that? We've got about We got about
Yeah.
a minute left, and I do want
Okay,
to say
yeah.
that we've got about a minute, and they will cut us off
Yeah.
at 15 after. So yeah.
Yeah, no, I just want to say that, yeah, we did a whole class and sometimes even a whole grade. So every student can do it at the same time on a Chromebook for the Melva assessment. And I'm not sure, Joe, if you want to talk about the ORF, how it's
Yeah,
administered.
Yeah, these were just in the research studies. We gave them the option, like, hey, do what you want to do. I was surprised. We did kind of informal survey. They liked smaller groups as opposed to like whole class. And even though, like, hey, you can get all your kids read here in a few minutes. They like the smaller group format where they're sent to like maybe a station, things like that. But ideally, it's kind of open to both. And yeah, I think technology always has issue, and as long as you have the audio, you're good, because the teacher can always go back and listen and score themselves, which is nice. If you lose that, that's a problem. But there's a lot, anecdotally looking at the data, there's a lot of features you can call that would flag a teacher to, hey, give this one another listen.
And with that, it is my unfortunate responsibility to make sure that we end on time. So I do appreciate everyone's conversation and the discussion. Please send us emails if there are other aspects that we weren't able to get to in the panel session. And thank you so much for your time and efforts and attending.